Hello everybody. This is the second of two lessons about partial fractions, and today we're going to look at some more complicated cases. And to be honest, we're not going to be looking at all the levels of difficulty that we typically would, because as we know, we're cutting back this year. But I think this will be helpful still to get slightly more complicated examples. And before I show you the partial fractions problem, I want you to think about this problem. So a good math problem-solving strategy is solve a simpler problem and to use the ideas of a simpler problem to guide you in a more complicated one. So let's say we had the fraction 7/8. And let's say that we got that fraction from adding or subtracting some other fractions. Well, what might those other fractions have been? Now, if we think about what we did with partial fractions last time, if we had something that was, say, 7 over x times x plus 1, then we had something over x. X was a factor of the denominator, and we had something over x plus 1 because x plus 1 was a factor of the denominator. So what if we use that kind of line of thinking and we said, well, this could be something over 2 because 2 is a factor of the denominator, and something over 2, that's another factor, and something else over 2 because the denominator factors into 2 times 2 times 2. So what do you think about that argument? Would that actually work? If you were adding these three fractions, would you get your denominator to be 8? No, you would not. What would your denominator be? It would be 2. So there's a problem with that. So what could we do instead? Well, is there a chance that you could have had maybe a fraction with a denominator of 2 and a fraction with a denominator of 4. 2 times 4 is 8. Nope, that's not it either, because what's the common denominator for those? It's 4. Is it possible that you had something with a denominator of 2 and something with a denominator of 8? Oops, let's make that a B. Is that possible? Yeah, maybe. Could be. Is it possible that you had something with a denominator of 4 and something with a denominator of 8? Maybe. Common denominator there would be 8. Is it possible that you had something with a denominator of 2 and something with a denominator of 4 and something with a denominator of 8? Maybe. We don't know, right? So we don't want to eliminate the possibilities. So what we're going to do, if we have a denominator of 8, is we need to have a denominator of 2, just in case, a denominator of 2 squared, just in case, and a denominator of 2 cubed, just in case. If one or more of those is not needed, then we'll get a numerator of 0, and we'll know that it wasn't needed. So let's extend this idea. Suppose you had something over x minus 1 cubed. What denominators would you need in your partial fractions? You would need a denominator of x minus 1. You would need a denominator of x minus 1 squared. And you would need, sorry, that should be a plus. And you would need a denominator of x minus 1 cubed. Now, do you actually need all three? We don't know. Maybe you only need 2 of the 3, and the other one will eliminate itself if you get a numerator of 0. Okay, we're going to work through 2 examples. I think this is notes number 50. And then after that, you have 4 homework problems. Okay, example number 1, separate into partial fractions 2x minus 3 over x minus 1 quantity squared. So according to what we just went over, we're going to separate this into one fraction with a denominator of x minus 1, so a over x minus 1, and then another fraction with a denominator of x minus 1 quantity squared, so b over x minus 1 quantity squared. Here we have our equation. We're going to multiply both sides by the least common multiple of the denominators, so we're going to multiply both sides by x minus 1 quantity squared. So on the left side of the equation, all we have is 2x minus 3, because the x minus 1 quantity squareds cancel. And then on the right side of the equation, the x minus 1, one of the x minus 1s is going to cancel with the one that we have on the bottom. So we're going to have a times a quantity x minus 1. And then for the other one, both of these are going to cancel with those, and so all we have left is b. Okay, so we want to solve this for a and b. And remember that last time we had two methods that we could choose from, so I'll demonstrate this one with both methods. So method 1 was to separate all the terms and to make an x term equation and a constant equation. So we have 2x minus 3 equals ax minus a plus b. And so for the x term equation, we have 2 equals a. Easy peasy. And for the constant equation, we have negative 3 equals the opposite of a plus b. And because we just found out that a is 2, we could write negative 3 equals negative 2 plus b. So b is negative 1. And remember, if you want to use method 2 instead, then you're going to choose a strategic value for x. I would say let's let x equal 1 and substitute that into this equation. And we get negative 1 equals a times 0 plus b. So now I know that b is negative 1. And then, okay, here's something that didn't come up last time when we were using this strategic substitution method. We had multiple numbers to substitute in, and that gave us everything we needed. Well, if you're looking at this one, x equals 1 is a great number to substitute in, but what else? There isn't another fantastic number, but you can use a pretty good number like 0 or 2 or something like that. So I'm going to choose let x equals 2, x equal 2. Substituted in the left side of the equation, I get 1, equals, substituted in the right side of the equation, I get a times 1 plus b. And I just found out that b was negative 1. So 1 equals a minus 1. Add 1 to both sides, and a is 2. Okay, so notice that we got a equals 2 and b equals negative 1, whichever method we used. So putting those into their fractions, we have 2 over x minus 1 minus 1 over the quantity x minus 1 quantity squared. What's that you say? You really feel disappointed when I don't check my answer, and you would really like to see me check this one? Okay, sure. Let's go ahead and combine these into a single fraction and make sure that we really get what we started with. So the first fraction we should multiply by x minus 1 over x minus 1 so that we can get our common denominator. And we don't need to do anything to change the second one. So our numerator is going to be 2 times the quantity x minus 1 minus 1, and our denominator is x minus 1 quantity squared. So our numerator is 2x minus 2 minus 1, and our denominator is x minus 1 quantity squared. So our numerator is 2x minus 3, and our denominator is x minus 1 quantity squared. And that, my friends, is the original problem. It works. Okay, let's do one more. Okay, now we're going to separate this. Notice that we have 2 factors of x and, bonus, 3 factors of x minus 1. Okay, so we have a lot of fractions to separate this into. 6x squared plus 1 over x squared times x minus 1 cubed is going to be equal to a fraction with a denominator of x plus a fraction with a denominator of x squared, because remember, we have to have all the multiplicities of that, all the powers of that factor leading up to the highest power we see in the denominator. A fraction with a denominator of x minus 1 a fraction with a denominator of x minus 1 squared and a fraction with a denominator of x minus 1 cubed. Okay, let's multiply both sides of the equation by x squared and by x minus 1 quantity cubed. So we will have 6x squared plus 1 equals a times x minus 1 quantity cubed. See, the x canceled with one of the x's. Then we will have b times x minus 1 quantity cubed. See, the x squared canceled with the x squared. And we will have cx squared times x minus 1 quantity squared. See, the x minus 1 canceled with one of the x minus 1's. And we will have dx squared times x minus 1. See, the x minus 1 squared canceled with two of them. And we will have e times x squared. See, the x minus 1 cubed canceled with the x minus 1 cubed. Okay, now, I don't know about you, but I really do not want to use method 1, where I multiply everything out and create all these equations. I'm going to use method 2. So let's choose a convenient value for x. Let's let x equal 0. This will give us 1 equals, we get 0, we get 0, we get 0, we get 0. The only thing left is b times negative 1 cubed. So we get 1 equals the opposite of b. So now we know that b is negative 1. Excellent. Let's let x equal what? What's next? Yep, you're right. X equal 1. And on the left side we get 7. And then on the right side, let me undo some things. On the right side, this will be 0. This will be 0. This will be 0. This will be 0. We just have e times 1 squared. So we have e. Excellent. Okay, we're out of fantastic choices for x. Now let's do some pretty good choices for x. How about if x equals 2? Now I'm going to speed this up a little bit, just for the sake of time. If x equals 2, we get 25 equals 2a minus 1. Remember, we know the value of b, and we could substitute it in that second part, plus 4c plus 4d plus 28. And then you're going to add 1 and subtract 28 from both sides, and you get negative 2 equals 2a plus 4c plus 4d. And then you can divide both sides of that equation by 2, and you get negative 1 equals a plus 2c plus 2d. Do you see where this is going to go? This is one equation with 3 unknowns. And guess what? We need 3 equations with 3 unknowns to solve a 3 by 3 system. So let's do this 2 more times with 2 more values of x. I'm going to let x equal 3. And I'm going to speed this up again. You can take it slower if you want. This gives us 55 equals 24a minus 8 plus 36c plus 18d plus 63. That simplifies to be 0 equals 24a plus 36c plus 18d, and that can reduce to 0 equals 4a plus 6c plus 3d. Okay, one more time. I'm going to let x equal negative 1. And that gives me 7 equals 8a plus 8 plus 4c minus 2d plus 7. Simplify that and we get negative 8 equals 8a minus plus 4c minus 2d. And then divide that by 2 and we get negative 4 equals 4a plus 2c minus d. Okay, would you look at that? We have our 3 equations with 3 unknowns. We have a 3 by 3 system, and we can solve that in so many ways. We could use substitution or elimination or Cramer's rule or the inverse matrix method. And I'm going to use the inverse matrix method. So I set up a matrix with my coefficients of A, C, and D. So for the first equation we have 1, 2, and 2. For the second equation we have 4, 6, and 3. And for the third equation we have 4, 2, and -1. We call that matrix A. Then we set up our variable matrix, we call it X. The variables are A, C, and D. And then we have an equals, and then we have our constant matrix, -1, 0, and -4. Those come from those 3 equations, and we call that matrix B. Does this ring a bell? It's been a while. Now, to solve for the variables, we take A inverse times B, and we substitute that into the calculator, and what do we get? We get -3, 3, -2. Okay, so let's put those into our fractions. We have A, B, C, D, and E, don't forget. So A was over X. So we have -3 over X. B was over X squared. And B is -1. So I'll just put a minus. -1 over X squared. C was over X minus 1. So we have +3 over X minus 1. D was over X minus 1 quantity squared. So we have -2 over X minus 1 quantity squared. And E was over X minus 1 quantity cubed. And E was 7. What's that? You're telling me you want me to check this answer? No, I'm sorry. Not this time. You can check it, but I see that my video is getting kind of long. Okay, great work, everybody. So we have partial fractions worksheet number 2. Check your answers, ask questions, send me pictures. And I'm going to post a worked out solution video for you just for a little extra help since some of these are kind of complicated. Thanks, everyone. Bye.